All right, everybody should now have the permission to record. All right. This is our last week in elasticity. Hopefully, you learned your lessons here and have a good background in the theory of elasticity. And as such, you distinguish yourself from those who have lesser knowledge in these basic tools of analysis of structure on a rigorous way and with a better accuracy. We talked about last week on simple tension and compression and showed you the equations that we developed there. An example of a bar being hanged and loaded by its weight. And also we looked into the bending problem and we worked through the equations. Basically, the equations of the stresses were the same, but the difficulty is to calculate the displacement here. If you realize the when you look into the displacement, and that is one thing that I would like to gain some potential capability to work through these equations. Basically, stresses are given from the stresses you calculate the strain, and strain given, then you write the equations that correlates the derivative of displacement with respect to strain. 3 equations for the normal strain, 3 equations for the shear strain, 6 equations that correlates u, v, w to epsilon x, epsilon y, epsilon x, gamma xy, gamma xz, and gamma yz. With the help of these equations, you should be able to calculate u, v, and w by direct integration. Realize we are dealing with partial differential equations. You have to get some basic knowledge on that. I've seen some questions being asked that it seems there is some misunderstanding or forgetful knowledge of some basic calculus. We are dealing with partial differential equation. We are dealing with total differential of a function and so forth. So get familiar with these concepts. So basically what we are doing in general with these problems is that we start to integrate one by one these equations. The one which is direct, for example, derivative of w with respect to z, which is the formation of the strain in the direction of the beam along the axis of the beam, is shown with epsilon z, and it's proportional to the distance from the neutral axis over this radius of curvature, which is basically moment over EI, moment of inertia times the modulus of elasticity. In the y and z direction, y and x direction, there is a Poisson effect. So the same strain multiplied by Poisson effect will give you the strain in x and y direction, and corresponding derivative of u with respect to x and v with respect to y. And the shear strains are all 0, and they are given by this. So we start with integrating the first equation. When we do integrate a function, which w, generally speaking, is a function of x and y and z. Okay, I just got a message. Do we have do anybody has the access to the or permission to record? If not, let me know. Maybe the old message that's just came to my attention. All right. If we look, generally speaking, these are functions of x and y and z. So w, like u and v, would be a function of x, y, and z. So partial derivative of this with respect to z is given. When we integrate it with respect to z, as shown here, the constant of integration would be a function of the other two variables. When we integrate with respect to z, the constant of integration would be a function of both x and y in three-dimensional space. These are the three-dimensional space. In two-dimensional space, we are dealing with x and y, but here, all the three parameters, x, y, z coordinates are in picture. Then we go look into the other equations, and what we did here, we substitute the results that we get here, w equal to x over rz plus w0, and substitute into the second and third equations of z. So we substitute w in this and that equation, and then expand it. We end up with this equation that gives you derivative of u with respect to z plus z over r plus this, which is a function of x and y, is equal to 0. We rearrange it, bring this to the other, these two terms to the other side, and integrate with respect to z. When we integrate u with respect to z, integral of this term with respect to z, we will have a constant of integration, again, that will be a function of x and y. And we call it u0 because it's u, the constant is referred to as u0, which will be a function of x and y. And similarly, with the next equation, a similar expression is obtained with the constant of integration v0 x and y. Once these are determined, once u and v and w are determined in terms of a variable, which is a variable, a function of z plus some constants of x and y. That's the way u and v and w are determined. Then we go and try to calculate these constants u0, v0 by substituting u and v in equation b into this equation. We have calculated u, we have calculated v, we now substitute them in this and that equation. And once it is done, we end up with this equation and that equation. One substituting into this equation, one into the other equation. Now, here is the moment that you have to make a decision. This is a decision-making position now. The first term is z multiplied by some function of x. The other two terms do not have z there at all. It cannot be equal to 0 for all values of z. For example, it may be equal to 0 for the value of z equal to 1 or 2, but it cannot be made for all the values of z equal to 0 unless the first term is 0 and this bracket is 0. Similarly with the other equation. And then, once that is determined, step by step, we end up with the case that shows derivative of w0 with respect to x twice is 0. Its derivative with respect to where is it? Also, derivative of this second term, this bracket should be equal to 0, and this other bracket on the other, this bracket should be 0, and that bracket should be 0. From there, if we make that bracket equal to 0, it is a function of x and y. Look, every term in this bracket is a function of x and y. When we integrate it with respect to x, what we get, u0 xy, integral of v nu x over r with respect to x, which becomes x squared over 2. But the constant of integration, because this is only a function of x and y, the constant of integration would be only a function of y. When we integrate with respect to y, now the constant of integration would be a constant, would be a function of x. Because here, u0 and v0 are only a function of x and y, not z. So once integrated with respect to x, constant here will be function of y. Once integrated with respect to y, constant would be a function of x. Having that in mind, rearrange it to get u and v as shown here. Now we want to calculate fy and gx. The only equation is left is the first equation here that says the derivative of u with respect to y plus the derivative of v with respect to x should be equal to 0. So we put u and v in that equation and make it equal to 0. And again, it's decision-making time. We have the first term here, which has a z in it. The other terms, they don't have a z in it. So the first term should be equal to 0. Then look at the other three terms. This first term is a function of x only. The other two terms is function of y. So the part which is function of x should be a constant. We call it minus alpha. The constant, the function of y would be considered the constant plus alpha. So once they are added together, they will cancel each other, and the total will be 0. Now, the first sets of equation says that, first of all, second derivative of w0 with respect to x is 0. Secondly, the second derivative of w with respect to y is equal to 0. One of them should be y. And also the derivative with respect to x and y equal to 0. That means basically w0 should be a linear function of x and y. It can be easily proven. You can integrate it with respect to x, then integrate with respect to y for each of these equations, and you make that conclusion. Where m and n and p would be a constant. So the solution would give you w0 as a linear function of x and y. Then look into the other two equations we developed, integrated, and you get the function gx and fy as a linear function of x and y. So we involve with 1, 2, 3, 4, 5, 6 parameters. 6 constants. 6 constants of integration. I don't know, in dynamics, if you remember, you learned that a rigid body motion in 3-dimensional space has 6 degrees of freedom. 3 degrees of freedom for translational motion, moving in X, Y, and Z direction. 3, rotational motion, rotating about X, rotating about Y, rotating about Z. So we have 6 degrees of freedom for rigid body motion. So any component that we have and it's loaded, we have to constrain it such that it doesn't move. And to do so, we need to prevent this 6 degree freedom motion of the body of your interest. The 6 degrees of freedom, if constrained, each would give you one equation. Therefore, there are 6 equations and 6 unknown, M and P, alpha, beta, gamma, for every problem. In this case, I consider, if this is my beam, I consider at the end point, at 0 point, X is equal to 0, Y is equal to 0, Z is equal to 0. That prevents translational motion of the beam at the end point. Then I consider rotation about X and Y and Z is equal to 0. That means the derivative of U with respect to Z, derivative of V with respect to Z is 0. That means an element, as shown here, a small element along Z direction, if you consider, would have a 0 slope. That is the condition for being fixed at one end. With these 6 degrees of freedom expressed, all the constant of integration can be calculated, and eventually you get the displacement U and V and W as given by these equations. U is given by this equation, V by this equation, Z, W in this equation. If you arrive at this solution, one way that you can check if your solution is correct, go put it back into the basic, the first equation. Go back, put the results into this equation. You have W, U, and V. Put in this equation, you should arrive at the same answer. And if not, then you make mistakes on it. Always it's good to check. Once we have the results, the other thing is looking into these results, as we talked about before. Looking into these results, you can see that on the cross-section side, if the beam is being, let me get my pen. If this is the length of the beam, and spent by the bending moment, I have a curvature. If this is the Z-axis, and I'm sorry, this is Z-axis, and that's Y-axis. I have a curvature in YZ plane. On the cross-section side, on this side, you can see you have an opposite curvature, upward curvature, as the beam is bent in YZ plane in that form. In the other cross-section, it would bend in this form. It's this format of a shape of a saddle. So that is what is usually referred to as saddle deformation of the beam. And if you look in detail of that deformation, you can see that the contour of the deformation on the cross-section would be as you can see, a hyperbola on the top and the bottom and everywhere else. And the equations of asymptote of the hyperbola is given by this. and the slope of the asymptote would be 1 over nu. So if you get a picture of the deformation, photoelasticity or so, from this picture, the slope here, alpha, would correlate to the Poisson ratio. That's one of the methods that we can measure the Poisson ratio of a material. It's a very difficult task to measure Poisson ratio directly because the deformation, lateral deformation, is not that easy to measure in a tension test. Now that we are made familiar with bending, the last thing that we would like to cover in this session is torsion. What we learned in elementary theory of torsion and mechanics of material, we just discussed usually the circular shaft. And circular shaft is a special case that when it's being torqued, all points in the plane would remain in the same plane and will remain perpendicular to the axis of the shaft. And subsequent twisting, circular cross-section will not be distorted. We have seen these pictures probably often in mechanics of material, and we develop the equations. We create shear stresses. Let me get my pen. We get the shear stresses all around at every circular cross section. And these shear stresses are proportional to the distance from the center of the shaft. Rho is the radius of the shaft, and R is the distance from the center. So the maximum shear stress would be, of course, when R is equal to rho, but at any other point as you approach to the center, the shear stress is decreased. And the torque is related to the shear stresses according to this equation that we usually develop in mechanics of material, T times R over J, where J is the polar moment of inertia, pi over 2 R into power 4 for circular shaft, solid shaft for the hollow shaft is given by the other equation we are all familiar with. And the shear strain, which is shown here, would be equivalent to R phi over L, where phi is the angle of twist here in this plane, and eventually the angle of twist phi in torsion is calculated by this equation TL over JG. These are what we have seen in mechanics of material. Now, what do we need to add here? So the stresses is again the stresses again are defined in the same format that we had in mechanics of material. Nothing different. Now, let us see if the elementary theory is an accurate solution of our problem. So we take that very same solution and we say that the shear stress is proportional to the distance from the center of the shaft. And G phi over L. Phi is the angle of twist. G is the shear modulus. L is the length of the shaft, which is a constant. All we are saying is that we will have a shear stress. Let me get the pen here. That at any location, for example, at this location here, the shear stress would be in that format. Its magnitude would be some constant times parts. And that shear stress is always perpendicular to the radius. So at any location, the shear stress would be, the direction of the shear stress would be in perpendicular to the radius. So it has two components along y and z, and each component is shown by this equation. This is the solution that we are deriving based on the simple mechanics of material. That the shear stress, if that is the circular shaft, shear stress at any point would be, the direction would be perpendicular to the radius, and its magnitude would be proportional to distance from the center of the shaft. That's all in this equation. Try this equation in equilibrium equations that we had. We can see all the equilibrium equations are satisfied. So the solution, elementary solution of torsional problem satisfies the simple equilibrium condition. Also, it would satisfy the compatibility equation. Do we know why? We have indicated before that if the stresses are linear function of x and y and z, as is the case here, compatibility equation often is, each term is expressed in terms of the second derivative with respect to x or y or z. And since these are linear function of x, first derivative would be a constant, second derivative would be zero. So all the equations of compatibility are automatically satisfied with the linear stress formation. So you can see the solution that we had from elementary mechanics of material would satisfy the equilibrium equations and compatibility equations. Now look into the boundary condition. The stresses produced here should produce no force on the circumference of that circular shaft, and they should produce equivalent stress on the cross section equivalent to the torque that is applied. And you can see, if you look into the component of the forces, these are the equations of on the boundary condition that we have developed before. Considering any element here, the effective external forces in x, z, and y direction should be all equal to 0 on the boundary of on the surfaces of this cylindrical shaft here, and the boundary condition is given by this equation. Sigma x is 0, tau xy, and tau xz components along the on these surfaces are also equal to 0 because at that location, the M and N, the normal to these surfaces, if you consider this shaft, any point on this would have a normal direction N, and normal to that would be in making an angle equal to 90 degrees or with the sine of the cosine of 0. So it would be 0. So you can see basically all the boundary conditions are satisfied. The next step, as we did before, we want to calculate deformation. Epsilon x, epsilon y, epsilon z, they are all 0. Shear stress in xy and xz direction, xy direction is 0. Xz and yz are given by the equation that we developed before. Substitute there, and you can calculate eventually in a similar fashion we did before. You can calculate u and v, and notice that w is 0. W is 0, that means there is no deformation in the direction of the axis of the shaft. That is, if I have a shaft like this, and a torque is applied, I do not have any displacement in z direction. W is equal to 0. That means planes which were a circular cross section that were plane would remain plane and do not warp. W being 0, it means that with a circular shaft, there is no warp. And that is only the case with circular shaft. That would not be the case if any other cross section is selected. If we have, for example, a rectangular cross section as shown here, and we expose it to a twisting moment, the cross section, the shaded cross section shown here, which was on a plane, after being twisted, will not remain a plane. We have some warping of that cross section. You can see, for example, this point moves this way, and this edge moves that way. And that means the plane would not remain plane, and we have certain type of a warp. With any torsional problem, any shaft, we would be able to find a central point that is the center of symmetry of that cross section, if it has a center of symmetry, which does not move, remain stationary. So in the case of a rectangle somewhere at the midpoint here, in the case of a circle, the center of the circle. In the case of ellipse, the center of the ellipse. Once the torque is applied, would remain stationary. So that center arc point would remain stationary. If the cross-section has symmetry, the center of rotation, or the twisting center, would coincide with the that location, center, geometrical center of the shape, if it has two axes of symmetry. If not, you have to go and calculate the twisting center of that cross section. So how do we formulate the problem for any cross section which is not circular? Any other cross section, as we mentioned, except the circular shaft, we have warpage. That means there is a displacement along the axis of the shaft. But that displacement would be only a function of x and y, and wouldn't be a function of z. That means the deformation of, say, this plane in front of the beam, or another plane somewhere here, or another one somewhere here, after the loading, would be identical. So the deformation or the warping would not be a function of z-axis. It would be only a function of x and y. And projection of any point on the cross-section would have a simple rotational motion from position P to P prime, very similar to the case that we studied for the circular shaft. The only difference is that we have warpage, that is the point P does not remain in the same plane, it moves up and down. But its projection on the initial cross-section would be similar to the rotational circular shaft, a simple rotational motion from P to P prime by the angle theta. So basically, the way we formulate the problem is that displacement in XY plane, initial cross-section of the beam, shown by U and V, would be just from point P to P prime, would be just a simple rotation. That's like a very similar to the circular shaft. It can be expressed as a function of zy and zx. So we begin the problem for the twisting of a circular shaft that displacement in x direction is equal to a constant theta times z times y, and displacement in v direction would be theta z times x. So displacement linearly increases if this is the shaft, and that is the z-axis. You can see it linearly increases as we go from the fixed end to the free end that we are twisting. As we go further away from the fixed end, the displacement in the shaft increases proportional to z, and also from a point on the cross section away from x or away from the y, it will change proportional to y and x. This is the beginning of the solution. Substituting them into the strain equation, you can see epsilon x is 0, epsilon y 0, epsilon z 0, gamma xy is 0. The only shear strain that is developed are gamma xc and gamma yc. We can see the equations are similar to the circular shaft. The only thing which is added here is the warpage, which is this term. We didn't have this term for the circular shaft. Other than that, it would be everything similar to the circular shaft. So, per Hooke's law, once the strain is defined, stresses are defined accordingly by this equation. And if we try to see if the equation would satisfy the equilibrium equation, we put it there. We notice that the necessary condition such that the equilibrium equation are satisfied is that this equation should be satisfied. So tau zx and tau zy placed here in that equation should be equal to 0. That is, by substituting these there into that equation, simplified, you end up with this equation. Again, you can see that W is a Laplace's solution. The second derivative with respect to x plus second derivative with respect to y is 0. That is the equation that defines the warpage on a non-circular shaft. And now look at the compatibility equation. There are 6 equations of compatibility because epsilon x, epsilon y, epsilon z, gamma xy are 0. The first 3 equations are 0. The 3 next equations, the left-hand side are 0. The right-hand side, these third terms are 0 because gamma xy is 0. So we end up with these 3 equations. If we expand it, it comes to this, and we substitute the values that we consider for tau xc and tau zy and work it through. You can see that equations of compatibility, they are all satisfied. So the solution we have accurately define the solution of a twisting of non-circular shaft because it satisfies the compatibility equation, it satisfies the equilibrium condition if this equation, if W is a solution of this Laplace's equation. To better formulate the problem of twisting, Prandtl defined a stress function. Again, we are talking of stress function. That means stresses are derived from that stress function. It is not stress, it is stress function. And I see a couple of students, just take the stress function as a stress. So we define the stress function phi such that its derivative with respect to y would be the tau zx and derivative with respect to x minus would be equal to tau zy. If the equation, if the function phi is defined in that fashion, you can see that it is automatically satisfied the equilibrium equation. And differentiating equation 1 and equation 2 that defines the stresses tau zx and tau zy with respect to y and x, and add them up, you end up with this equation. That it says Laplace Prandtl stress function phi should be selected such that this equation is satisfied. Second derivative of phi with respect to x plus second derivative of phi with respect to y should be equal to 2g times theta, which is a constant. Let us look at the boundary condition. We satisfied the elasticity equation. We want to see if the solution would mean it would be the equation for the boundary condition. It would be equation for the specific geometry of the cross section that we have. Look at the boundary condition equations that we had before. Everything is 0 except the tau xz and tau yz. So sum of tau xzl plus tau yzm should be equal to the force in z direction at any point here on that boundary, but the force in z direction is 0. So tau xzl plus tau yzm should be equal to 0. But tau zx is derivative of the stress function with respect to y, and tau zy stress function with respect to x. Substitute into this equation. And notice L and M from the geometry here is the cosine of the angle between the normal to the cross section N and x-axis and y-axis, and that is equal to dy over ds or dx over ds, where ds is the element along the periphery of the cross section. Substitute that into this equation for the boundary condition, you would find that we conclude that the derivative of phi with respect to s is equal to 0. That means phi is constant along the boundary condition. So here we are. Suppose we have a cross section of any shape, and the twisting moment is applied. We have to find the phi function, stress function, such that it would be constant along the boundary. So phi should remain constant along the boundary for every value of x and y. Phi should remain constant on that boundary. And let us see how we can solve specific problem of interest. This is again another format of showing that stress function is constant on the boundary. And when we, that is on the boundary of the surface, and when we integrate the stresses, you would find that the again in another format. Phi1 is equal to Phi2, and therefore phi would remain constant on the boundary. Finally, I can calculate the moment of these stresses about the center of twist, and that moment would be equal to the twisting torque T, which is applied. Substitute the stress function for the tau zy and tau zx, and do the integration. There is a little bit of a math involved here, that we do some integration by part. I'm not that much interested in the math, but eventually you come up with the final solution that the torque would be twice the double integral of phi dx dy. So, solution for the twisting of any cross-section should be such that the stress function should remain constant on the boundary, and the integral of that stress function over the cross-section should be twice, or should be 1/2 of the torque applied on that cross-section, on that. Let us study the simple case of an ellipse. Suppose we have an elliptical cross-section, and we want to calculate the shear stresses in this elliptical cross-section. It's not a circular cross-section, therefore there should be some warping. So the first step is to find the stress function. I know that stress function should be such that its value on the boundary of that ellipse is equal to 0. The equation of the ellipse is given by this expression. So basically, if this is x, y coordinate system, and that's my ellipse, x squared over a squared plus y squared plus b squared over b squared is equal to 1, where a is half of the major and b half of the minor axis of the ellipse. That's the equation of ellipse. So if I consider any point on the ellipse with the given x and y, x squared plus over a squared plus y squared over b squared minus 1 should be equal to 0, because that's the equation of ellipse. So that parenthesis here is 0. So if I choose my phi function as a constant times that expression, that is the equation of the ellipse, phi should remain 0. And 0 is a special case of a constant. So as such, I am guessing that for the ellipse, I can select a stress function v is equal to k times x squared over a squared plus y squared over b squared minus 1. With that in mind, it is just letting you know, this is a guesswork. I could have chosen, for example, k times x squared over a squared plus y squared over b squared minus 1 into power 5. That function still satisfies the boundary condition because phi would be 0 in this case as well, right? Why should it be 1? It could be 5, it could be 10, it could be any number. But for the time being, let us assume it is a linear function of the equation of the ellipse. Is that the real solution of this problem? It satisfies the boundary condition. But it also should satisfy the elasticity equation that we developed for the Prandtl stress function. This equation should be satisfied for every value of x and y. So getting the second derivative of this with respect to x, adding that with the second derivative with respect to y, should be a constant h. So the second derivative of x squared would be, first derivative would be 2x, second derivative would be 2. So it would be 2 over a squared. Second derivative of y with respect to x would be 0, and that constant would be 0. So that is the first term. Second term, second derivative of first term with respect to y would be 0. Second derivative of this second term with respect to y would be simply 2 over b squared. That times k should be equal to h, the constant h. And you can see, if I choose my k, according to that equation, which is simplified to this, then the stress function satisfies the Prandtl equation with this differential equation. So indeed, this would be a proper stress function that clearly defines the state of the stress for the elliptical cross-section, because it satisfies the boundary condition, it satisfies elasticity equation, that means all the equilibrium and compatibility equation. And now what is left to do is to get the derivative of the stress function with respect to x twice and with respect to y twice to calculate effective stresses. But before going there, we need to calculate the constant h. Constant h comes again from the other equation that we developed, the integral of phi over the cross-section of the ellipse times 2 should be equal to the torque apparent. So we just substitute phi from the equation that we obtained here, put it here, do the double integration with respect to x and y, and notice that the derivative with respect to derivative of x squared dx dy would be a moment of inertia about y-axis, and the other one moment of inertia about x-axis, and this one would be simply the area moment of inertia of ellipse about x and y, and the area of ellipse are known. You can look into the tables and get the values and substitute there, and simplify. You find that h is given by that expression. Substitute h there, and that is the final solution for this stress function. This is stress function. still not the stress. Stress function, that means derivative of phi twice with respect to, say, y square would give you the tau xz as derivative with respect to x square gives the tau yz with a negative sign, something like that. Look into the equations. And that's what we did. Next page. Derivative tau zx, derivative of phi with respect to y, derivative of z with respect to x, and we have the phi, we get the derivative, and from there we get the stresses. So this is the equation for the stress, tau zx and tau zy. The stresses, these are the projection of the stress in zx and zy direction. If we want the total stress as a vector, would be sum of these two, which is equal to that. And the maximum stress can be calculated to be 2t over pi ab squared. And from the previous equation that we generated here, where is it? Theta is angle of twist. Angle of twist is h over 2g, and h we have calculated in this page to be that value. So from there, eventually we calculate the angle of twist for the elliptic. So this is the final solution. Now that the shear stresses are determined from these two equations, we can calculate the warpage. And you can see the warpage is given by this expression. So at the midpoint, there is zero deformation in z direction, so W would be zero at the midpoint. In this zone, it is bulging upward. In the dotted location, it's going downward, and as such, the cross-section deforms. Notice if A is equal to B, that means the ellipse deforms into the shape of a simple circle, then the warpage W would be equal to 0. B equal to A, the warpage would be equal to 0. So we have warpage if it is ellipse, if it is simplified to a circle, it becomes 0. You can consider any fancy cross-section. And in this case, I am considering a triangle. And see if the same trick works with a triangular cross-section. A triangular cross-section equilateral with the equal sides, as shown below. So equations of each side is given here. X plus square root of 3y minus 2 over 3h. It's just a simple geometric relationship that gives the equation of the line AB, AC, and the line BC is with the constant x at the distance h over 3. So if I multiply these three expressions, and phi function would have been chosen as a proportional to that expression, on the boundary everywhere it would be 0, because on each boundary one of these terms would be 0. So it satisfies the boundary condition. Express that formula into this equation, elasticity equation, you can see it is simplified, and it is simplified so that variables would disappear. 6x cancels out with the 6x, and we end up with a constant value. And that constant k can be calculated, and eventually your stress function can be defined. The twisting moment, as we did with the ellipse, can be calculated by double integration, and substituting into the results, you get the shear stress and the total shear stress and maximum shear stress. Just a little bit of the math. However, don't get too excited with this method, because if we want to apply the same thing with a rectangular cross-section, it doesn't work. Why? Because the boundary of that rectangle, each line here, this line, is x minus a over 2. This line is x, or the other line here, x plus a over 2, y minus b over 2, y plus b over 2 are the top and the bottom lines there. So if I choose the stress function, a constant, times this boundary condition, it will satisfy the boundary condition. So everywhere it will be 0 on the boundary, or constant. But when I get that expression and put it into that equation, partial differential equation, I end up with this expression, which would be a function of x and y. That means it is not constant. So this is not the solution of the problem. It worked for the ellipse, because at the end, when you work through that equation, it came up to a constant value. It worked for equilateral cross-section. For the rectangular cross-section, the stress function selected here doesn't work. So another stress function should be selected. It's been shown that a Fourier format of the a Fourier series format of the boundary condition can be selected such that it would satisfy the boundary condition and the also the elasticity equation of compatibility and equilibrium. The results is shown here. I'm not going into detail how we develop that result. It's just some sort of mathematical work, but you can try this stress function there, and you can see it satisfies the boundary condition, and it also satisfies the stress function. Once the stress function is defined, we can get the derivative with respect to x and y, calculate shear stress tau xc and tau yc. And from there, we can calculate maximum stress and maximum twisting length. In these expressions, we have the parameters alpha and beta, which needs to be calculated for any aspect ratio of the rectangle. And here in this table are the constants alpha and beta for rectangular cross-section. You can see when A is equal to B for square for the square cross section, beta and alpha assumes this value, which are different. As we go along the line and make it a narrower rectangle, and eventually at the bottom we have a cross section which is sort of a line cross section. The thickness would be very small compared to the length. So A over B, A would be much larger than the B, so B would be almost 0, so the ratio would be infinity. In that case, beta and alpha are equal, and in fact it is equal to 1/3. This is the solution for rectangular cross section, and this is the problem. Let me clear the annotation. That I would like you work as your homework problem, and that would be also the second part of your final exam. Just this one problem, which is discussing the case of the torsion of a cross section which is not circular, but is made from a circular shaft which has a circular part. So this part is cut away from the circular shaft. And we want to calculate stresses and angle of twist for this cross section. The stress function I am suggesting is given here. Show me that it would satisfy the boundary condition. Show me that it would satisfy the stress function. And from there, you calculate stresses and deformation. It will be a simple problem. It will be very similar to the cases that we studied here. So you go and review the case of this ellipse and the triangular shape. It would be on a similar shape. So this is one of the cases that a closed solution can be obtained by a given stress function. The stress function that is defined here should be an equation that satisfies the boundary condition at any location. With this, we come to the end of our discussion today and lecture that we have today. On Thursday, we are just going to review the whole subject that we studied, answer your questions on different project problems that you have, and that would be the end of our elasticity course. So remember, look into this problem, get the solution for this problem, together with the problems that we mentioned before. That constitute your final exam, and all you need is to work through these and submit them just before or at the time or at the day, on the day that the final exam is set for the theory of elasticity. Any question? All right, if not, say goodbye, and if you have further questions, you can come back to me during the office hour in an hour and a half after I finish my next class. All right, take care. Bye.